I'm going to give you a little tour real quick of what we have done so far in Calculus AB. From the beginning of the year until now is our halfway point. I'll tell you, no secret here, just to keep myself organized and make sure that I reference the right section numbers, I'm just looking at the table of contents of our textbook, so that's a good reference for you. We've done material from chapters 2 through 5. Chapter 1, what happened to that? Well, that's just a review of pre-calculus and algebra kind of stuff. So we didn't mess with that. So in chapter 2, that was about limits. Now, with all of these sections and chapters, the best thing that you can do is go back and look at old assignments and assessments and see, look at a few problems and do I remember how to do that? Could I still do that? All those things are going to show up on both the semester. We don't have an official semester exam, but I am going to give you a test. It doesn't count like an exam grade, it just counts like a test. At the end of this course, you might take the AP test, or if you're taking it for dual enrollment, you're going to take a final exam. It's going to count for a big chunk of your grade. And it's going to go all the way back to Chapter 2, limits. So you can't just push this off and be like, oh yeah, that was a long time ago. Don't care about that anymore. You best be caring about this. What are some of the things that we learned how to do with limits? I think we need to make sure that we understand limits from looking at graphs. And remember that some of the basic things like when does a limit exist and when does it not exist. So can you have, for example, what if you have a function that's coming into a point like this, but the point's in the wrong place? Does this limit exist? Yes, and it's this, whatever this number is. If there's a hole, it doesn't matter where the actual point is or if there is one at all. This would still exist if it was like that. This exists. What about if you have something like this? Does this one exist? No, because the two sides have to be approaching the same thing. You can do the one-sided limits, like when x approaches 0 from the positive side and the negative side. You can do that sort of thing. There are vertical asymptotes, for example. What about this? Does the limit exist here? It doesn't exist, but we usually say that it's infinity, right? And of course, if you have a situation like this, then we have to say that that does not exist. So just understanding, looking at graphs, what limits are, what exists and what doesn't, that's important. And what else we got? How to compute limits. And I'm going to call that limits with algebra. That was when we did factoring and cancel. Algebro. That's funny. Remember that dude in your algebra class? That algebro. So limits with algebra, like factoring and canceling and stuff like that. So real quick example. What's the limit as x approaches 2 of x squared minus 4 over x minus 2? Well, that's x plus 2. X minus 2, and then the x minus 2's can cancel, and then you can plug the 2 in, and it's 4. And we understand if we graph that, the fact that that canceled out means that it's a situation where there's a hole in the function. That's an important thing to know. We did limits at infinity. What's happening as x approaches infinity? You can check back in 2.3, look at your Chapter 2 test for some examples of that. Section 2.5 was about continuity. What does that have to do with limits? Well, it turns out that we define whether a function is continuous or not using limits. So a function is continuous if there's no whole, jump, or vertical asymptote. So how do you make sure that there are no holes? You make sure that there are no holes by saying that the limit as x approaches some value c, wherever we're checking out if it's continuous or not, of f of x. We need this to exist. If that limit exists, then you can't, that gets rid of the possibility that there's a vertical asymptote, right? If this limit exists and it's a number, and that makes sure that there's no jump, right? Because if the limit exists, that means it must be coming into the same thing from both sides, and that the limit as x approaches c, f of x, is actually equal to f of c. So in other words, the place that it's coming into, like when you actually get there, the point is in the right place. So that's a way of understanding the continuity of functions in terms of limits. But that's what continuity means. No holes, jumps, or vertical asymptotes. So if you've got like a piecewise function, calculus teachers love piecewise functions because you can talk about whether the two pieces actually link up or not. And then we did some stuff with trig functions, limits with trig functions, and you can go back and look at that in your notes. One of the big results was that the limit as x approaches 0 sine x over x is 1. Now that we know L'Hopital's rule, you could do that, and it's arguably easier, because you could just say, we didn't know this back in chapter 2, didn't even know what a derivative was, but now we can say, okay, since I plug in 0 and I get 0 over 0, I can do L'Hopital's rule, which says the limit as x approaches 0. Take the derivative of the top, derivative of the bottom. Not doing the quotient rule, I'm just using L'Hopital's rule, which says straight up take the derivative of the top, and then take the derivative of the bottom, and then try again, plugging your thing in. Cosine of 0 is 1 over 1, it's just 1. So that's easy now. All right, chapter 3, this is huge foundations of calculus here. This is learning to take derivatives. Sections 3.1 and 3.2 were the understanding how we define definitions of the derivative. There's 2 of them. You can look back at your quiz for what those are. There's the there's the h approaches 0 version and the x approaches c version. It was the first question, I think, one of the first questions on your 3.1, 3.2 quiz was about that. And then in 3.3 through 3.6, we got some derivative rules. 3.3 is the power rule. That's like the one that says take the exponent, bring it down to the front, and then knock the exponent down by 1. Section 3.4 was the product and the quotient rules. Section 3.5 was the derivative of trig functions. Better have those memorized. And section 3.6 was the chain rule. So what if you have the sine of x squared? What if it's not just an x on the inside of your function? We call those composite functions in the language of math. And then 3.7 is related rates. You can review. That's a little corner of calculus that gets forgotten about sometimes when we're reviewing. You can look back at your notes. You've got to find some equation that relates the variables that you're interested in. It usually comes from geometry, and then take the derivative of that equation. You get little dA dt's or d volume dt, whatever, because things are changing with time. Go back and look at the examples of that. And then all throughout this, we've been writing equations for tangent lines. It's one of the things that we practice. But 3.8, we really looked at using tangent lines and actually using them to find approximations. So once you have a tangent line, then you can actually use that instead of the function to find values that are not exactly what the function is, but they're close. Okay, chapter 4 was more derivatives, stuff that we didn't get to in chapter 3. And what was that? 4.1 was the what we call implicit differentiation. This is when you have x's and y's mixed up together, and you don't want to solve for y, or you can't solve for y. So things like y squared equals sine of x plus y, and then you take the derivative. That's the derivative of y squared is 2y dy dx. Every time you take the derivative of something with a y in it, a dy dx pops out. Derivative of sine x is cosine x, and plus the derivative of y is 1 dy dx. And then you get all the dy dx's on one side, factor, and solve for dy dx. Go back and look at examples from there if you need to. And then in 4.2 we did derivatives of log functions. Derivatives of log functions. In particular, we're interested in natural log because the derivative of natural log is 1 over x. Now, of course, you can combine that with any of the rules from chapter 3, and we did in a lot of those homework problems, so you need to make sure that you're comfortable with that. In 4.3, we did derivatives of exponential functions. Hey, e to the x is a pretty cool function because it's its own derivative. And then derivatives of the inverse trig functions, right? In particular, we want the derivatives of sine inverse, cosine inverse, and tangent inverse. Those are the ones that come up a lot for us. Better know those. And I think we also did inverse functions in general, including the trig ones. So I'm going to make sure you review that. I think 4.3 that the notes were broken up into 2 parts there. 4.4 was L'Hopital's rule. Pretty cool. Easy way to evaluate limits. If you got a 0 over 0 or infinity over infinity, you can just take the derivative of the top and the bottom of your limit and then try again. And that was a pretty short chapter, only 4 sections. And then we're halfway through chapter 5 right now, first 4 sections. In all of those sections, I think we can summarize all of 5.1 through 5.4 is like analyzing functions using the first and second. I think that's how they spell that word in England. We use a Z, don't we? Analyzing? Yeah, I think so. You can spell it with an S. Still English. And the first and second derivative. So the first derivative tells us whether a function's increasing or decreasing, and this tells us about its concavity. So in general, we're thinking about finding maximums and minimums, right? Because increasing, decreasing, stuff like that. And intervals of concavity, positive second derivative, that means you're concave up. Concavity, inflection points. Definition of an inflection point is where the second derivative changes sign. Inflection point, oh dear. Hopefully not school. Inflection points. And stuff like that. And that's where we are at. So that will direct you to the right. I mean, you look at the table of contents yourself, but that'll help you figure out where you need to go. So I've got a big review assignment that you're going to work on, and I'm going to index it by what section, so we can kind of go through it in order and know what to expect when we take a little review test. All right, cool.